Welcome back to ECE 501B. This is our final day for Chapter 5 is the plan, and we may not get all the way through, but it's on you if we do not. But what we will try to do is at least get to the real vector case, or I'm sorry, the real eigenvalue case. But we'll start where we left off last time with this example of an upper triangular matrix and see how that actually corresponds to having some invariance properties, meaning when we start in one direction or in one plane, or depending on the dimensions, once we start in a particular vector, then we will map back into that vector or vectors that sort of precede it in terms of the invariance properties. That will hopefully be a little bit more clear as we go. That then leads us into proposition 12 in chapter 5, which does talk about upper triangular matrices and these invariant subspaces. We'll go over a proof. It essentially makes three statements equivalent, proposition 512, concerning invariant subspaces. We will then do proposition 16, which says that our linear map associated with T, if it's upper triangular, then we can invert that matrix if and only if all of our diagonal entries are non-zero. Proposition 18 says that the eigenvalues are on the diagonal. We'll see what happens now. The eigenvalues are on the diagonal of an upper triangular matrix. Then proposition 20 says if we have distinct eigenvalues of the same dimension as our underlying vector space, and remember, for these operators, we really only have one underlying vector space. We're starting and returning to that, and the operator is then living on that vector space. If we have n distinct eigenvalues, then that matrix is actually more than just upper triangular. It can be diagonalized. That means we can just look at the eigenvalues on the diagonal of that matrix, but that's only if we have distinct eigenvalues equaling the dimension of our underlying vector space. That's proposition 20. Proposition 21 starts equating these different properties. Our matrix is diagonalizable if and only if we have a basis of eigenvectors. And if we have a basis of eigenvectors, we can use those actually in a direct sum decomposition of our underlying vector space V. And that's all those are properties then of the preceding results in chapter 5. And as I said, we have some results with real vector spaces that are not as inclusive as complex vector spaces, because we've seen examples of even 2 by 2 matrices that don't even have eigenvalues for real vector spaces. Let's now return to the example that we had last time, where the basis that we're using is our standard basis in 3 space, and it's the real 3-dimensional space. And suppose that the mapping T has a matrix representation that is indeed upper triangular, and we have on the diagonal 2, 4, and 5. In the top row we have 2, 3, minus 1. In the second row 0, 4, 1, and in the bottom row 0, 0, 5. This should be what we've already looked at. Last time we found the associated eigenvectors for those 3 eigenvalues. Maybe we didn't find that one, but that was homework for you to try to determine the direction of your third eigenvector associated with the eigenvalue at 5, or with the eigenvalue at 5. Now we can actually look at this upper triangular matrix and see if, let's say, we operate on these three vectors, just our standard basis vectors, with that upper triangular matrix. Let's see what happens relative to where the output vector ends up. If we apply that mapping A to V sub 1, then really what V1 is saying is just pull off the first column in A. That's really what V sub 1 is saying. Doing that says, oh, we have 2, 0, 0. But that's just in the span of 1, 0, 0, which is the vector where we started this process. And that's then in the span of V sub 1. Meaning if we start, let's say, in the x direction with this upper triangular matrix, we are going to stay on that line or on the x-axis. That's what we're saying with that first observation. Suppose now we say, what if we operate on that vector, or a new vector, v sub 2, which is now, let's say, in the y direction. Then when we operate on that, that's like extracting the second column. And doing that, we pull off then the output of applying A to V sub 2 is just 3, 4, 0. And 3, 4, 0 is just in the span of the x and y plane. 1, 0, 0 and 0, 1, 0, reading from top to bottom in those vectors. And that's now just the span of V sub 1 and V sub 2. You can maybe start to see this pattern of the span that we are starting to live in is growing, but initially it's as small as it can be, V1, then it increases by a dimension, V1, V2, and now you can anticipate what's going to happen when we apply that same matrix A to V sub 3, which is now in the z direction. That now pulls off the third column in A, which we can form by a linear combination of V sub 1, V sub 2, V sub 3 with the appropriate scalars, minus 1, 1, and 5, respectively. And that says then that this operation of A V sub 3 is in the span of V1, V2, V3. Again, we're just adding more vectors to where we live. And that now says that if we started with something in the z direction or in the z coordinate, we will be in the full R3, so it's invariant to something in that space. If we started in the xy plane, we will stay in the xy plane. We won't jump up into the z coordinate. And if we start in the x direction, we will stay in the x direction. So we have some invariance, and this invariance is really sort of growing in dimension. We start in the x direction, then we start in the x, or then we say, let's try the xy plane, and we stay in the xy plane. Finally, if we include the third coordinate, then we're playing in the whole space, but we're invariant within that whole space. That then leads us to this proposition 12 in chapter 5, which says if we have this linear map or this linear operator on the vector space V, and suppose that we have a basis V sub 1 up to V sub n on that vector space, then we can actually show the equivalence of three different statements. The following are equivalent. We now have a linear operator and we have a basis on our vector space. If either of these three are true, then the other two statements are true, is really what we're saying. One, or A, is if the matrix representation of that linear map T using the basis V1 through V sub n is upper triangular, then that's equivalent to saying that this map, linear map, or this operator operating on V sub L will produce a result that's in the span V1 to V sub L for each L equal to 1 to n. So the first statement says, if you found a basis where your matrix is upper triangular, then you could also have this invariance property. Or if you have the invariance property with a particular set of vectors, then you can produce an upper triangular representation of that linear map. The final statement is that the span of V1, V2 up to V sub L is invariant under this linear map T for each L, where L could be 1. This is now this expanding invariance scenario that we just illustrated with the previous example. That's why I gave you that previous example, so that you would have an example that you could maybe think about in seeing this sort of abstract description of what's going on. But you're essentially now saying, oh, if I am given V1 and V2, then the way that those have been ordered will produce an upper triangular matrix, and if they do, then I can live in the span of V1 and V2 if I operate on those anything in those vectors with this linear map T. So let's show that, and we're going to show that a little bit more extensively than we need to. If we needed to show that those statements were equivalent, we could basically say A implies B, B implies C, and C implies B, or C implies A, and that would show that they're equivalent. We're going to actually, or I'm going to show that A is equivalent to B, if and only if, and B and C are if and only ifs. And then we can basically go any direction we want. That's the idea. Let's first show the equivalence of A and B, which I'm writing A double arrow B. Question? So now we are basically saying that the upper triangular matrix has to exhibit the particular structure that we've identified, that it's all zeros below the diagonal. You can't rearrange your columns. Then we lose all this invariance behavior. So we would have to associate particular vectors relative to that ordering, or to produce that upper triangular behavior or structure. And so the question, I think, was, if we have an upper triangular matrix, can we shuffle the columns? And my answer is no. Then you lose your invariance properties, which is what we're trying to preserve. So if you can convert, the question was, what if it's not upper triangular and you convert it to upper triangular? Then we're calling that an upper triangular matrix. We're saying that now, depending on how you order those vectors, you can produce an upper triangular matrix. So if you can find a matrix that you can convert to become upper triangular, then that's an upper triangular matrix. And it may require that you have certain vectors in the right order, but it is upper triangular. And that's what this statement A is essentially saying. It's saying you now have this ordering of basis vectors, V1 through Vn, that's producing an upper triangular matrix representation for the linear map T. So now the question was, if you reorder the basis vectors, is that going to swap columns? And yes, it will. And that's going to mess up these B and C arguments. Now we won't be able to have this sort of growing behavior of invariance, starting on a line, then a plane, then in 3 space, then in 4 space, etc. So we need to preserve those properties or ordering, and that's why we have T of V sub L, and we could say T of V sub 1 is contained in the span of V1. So now that's the one direction. Then if we go up to little l equal 2, then we're saying now we're living in this 2-dimensional plane or space in maybe R10 or C10, whatever we're playing in. Is that clear? Now what I'm going to try to do is show that A implies B and B implies A, or those two statements are equivalent. First, let's go A implies B. And now let's consider the matrix representation of this linear operator capital T, and consider that matrix. Considering that matrix, the nth column, remember how that was created. The nth column of the matrix representation of T is the expansion of T V sub L in the basis that we have agreed that we're living with, V1 through V sub n. In the basis V1, V2, up to V sub n. But if A is true, then we said statement A said our matrix is upper triangular. If we have an upper triangular matrix, then the nth column in that upper triangular matrix has a very specific structure. It's 0 below the diagonal and potentially non-zero above the diagonal, and the diagonal entry we're going to keep there. So the nth column of an upper triangular matrix looks like, and now what does that look like? If our matrix is upper triangular, it depends on what L is, but let's say L is somewhat large, so that now we have all of these potentially non-zero values, but everything below L is zeroed out. There are our L potentially non-zero elements, and here we have n minus L elements. This is the nth column of our matrix representation. Or we could say that that's now this, using our notation, it's the nth basis vector represented in terms of all the other basis vectors, and so this is now the first basis vector, or the scalar multiple of the first basis vector that is needed to represent the nth column in T v sub L. Then we have A to L all the way down to A sub LL, and below that, 0. That's the matrix representation of an upper triangular matrix. If we do have an upper triangular matrix, which is what we're assuming is true from statement A. What does that say? Well, that now says that those are the scalars that weight our basis vectors, meaning we now have A sub 1L times V1 plus A sub 2L times V sub 2 up to A sub LL times V sub L plus 0 times V sub L plus 1, etc., with the zeros up to V sub n. But we now know what that basically is saying. Now we're saying that T v sub L lives in the span of these first L vectors. That's what that's saying. This means, or this representation, that T v sub L is in fact expressible in terms of only basis vectors 1, 2, up to V sub L. Or T v sub L lives in the span of V1 V sub L, and that's true since we didn't specify a particular value of L. That's true for all L from 1 up to little n. And that was really statement B. So that now says that A does imply B. Let's now go in the other direction. Let's say that we now have B, and let's show that that implies A. B now says that we have the following. T v1 is in the span of v1. T v sub 2 is in the span of v sub 1, v sub 2. This is what statement B is saying. We have all these sort of nested spans going on. T v sub L is contained or belongs or lives in the span of v1, v2 up to v sub L. Then we could also say that, well, if that's the case, then I can create TV sub 1 as a linear combination of v1. I can create TV sub 2 as a linear combination of v1, v2, and now I'm just going to get very particular with how I denote those linear combinations, so that those subscripts on my combinations will naturally want to live in the appropriate matrix elements so that I can now build a upper triangular matrix. Meaning, now I can say that T v1 is, let's say, alpha 1, 1, v1. T v sub 2 is now alpha 1, 2, v1 plus alpha sub 2, 2, v sub 2. Meaning I'm going to take some multiple of v1 and some multiple of v2, and I'm going to simply combine those with these scalars, alpha 1, 2, alpha 1, sub 1, meaning what's the scalar multiple of vector 1, and this is for representing t v sub 2. And I can just keep going with that. T v sub 3 is alpha 1, 3 v1 plus alpha 2, 3 v2 plus alpha 3, 3 v3, etc. down to t v sub l is now alpha 1l v1 plus alpha sub ll v sub l. And I can now use those alphas to create a matrix that would then post-multiply my basis vectors, and that's really what this matrix representation is in the basis v1 through v sub l, which implies then that I have this matrix alpha 1, 1 and nothing below that to create tv1. To create tv2, I needed alpha 1, 2 and alpha 2, 2, and nothing beyond those two. To create tv sub 3, I needed 3 non-zero, potentially scalars, and I could just keep going. Alpha 1L, alpha 2L, down to alpha sub LL, but 0 below that, and then I have dot, 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 alpha sub 1N, dot, 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 alpha sub NN, and these are now dotted, and these zeros are dotted. Is that clean or somewhat clear the way I'm denoting that? All of my similar subscripts, 1, 1, 2, 2, 3, 3, those are all potentially non-zero, and everything below those are 0. So that now says that this matrix representation of T is in fact upper triangular, or B now implies A, and we just showed earlier that A implied B, and now we know that A is equivalent to B. Now we need to throw a C in there, and let's just go ahead and look at B if and only if C. Again, it's a little bit overkill, but we get to sort of play with different properties or proof techniques. Let's now show that C actually implies B. And let's do that by a contrapositive argument. Meaning, if we're trying to show that C implies B using a contrapositive argument, what are we assuming? So now we have, in our thinking, capital A implies capital B, where now little c is capital A, and capital B is little b. Not capital 1 anywhere. Capital A and capital B. What did we assume in a contrapositive argument? You remember? We negate the result and then use that to show the negative of the first statement. We are going to assume then not B and use that to show that not B in fact implies Maybe I'll write that out. Implies not C. That's our strategy. And B was the fact that the linear map T applied to V sub L was in the span of V sub 1 up to V sub L. Now we can say that's not the case. If TV sub L is not in the span of these first L basis vectors, V1 through V sub L, for each L, then the span of V1, V2, V sub L can't be invariant, since TV sub L is going outside of those vectors, then it's mapping beyond those, and so that spanning subspace is not invariant to this linear map T. If TV sub L is not contained in the span of the first L vectors, then the span of those first L vectors can't be invariant because this linear map T acting on a vector in the span of V sub 1 up to V sub L produces a vector that's not in the span of V sub 1 up to V sub L. And that's our contrapositive argument. That is basically not C. We needed this map to be invariant in this span of V sub 1 through V sub L. Let's now look at the other direction. Suppose now we want to show that B implies C. Then if B, then C, by definition, of invariance. By that, we know from B that we have TV1 is contained in the span of V1, TV sub 2 is contained in the span of V1, V2, and that just keeps going up to TV sub L is in the span of V1 sub L. And if that's the case, then all of these V sub L's are invariant under this mapping T. We don't get out of that spanning set V1 up through V sub L. Therefore, V1, V2, V sub L is T invariant. Or B implies C, which now says that B, if and only if C, and now we're done. We can start with any of those statements and show that it's equivalent to any of the others with any kind of circular argument. Let's now talk about some of these upper triangular matrices, or simply examine some statements about upper triangular matrices. And we aren't going to necessarily prove all of these, but if you want to see that, you can find those in the textbook. To fill in the justification of these. We're now trying to just sort of understand what some of these statements give rise to or provide us with in terms of information. First, let's look at theorem 13, which says given V, and now we are going to specialize this vector space to actually be a complex vector space. Given V, a complex vector space, and a linear operator T on that vector space, then there is a basis of that vector space V where the matrix representation of that linear map has upper triangular form. So if we're now allowed to live on a complex vector space and somebody gives you a linear operator on that vector space, then you can find a basis that will actually produce a matrix representation of that linear map that's upper triangular. Now that's definitely not true for a real vector space, so we have to restrict this or allow for this more complicated structure, which is this complex vector space. This is not necessarily true for real vector spaces. Let's see if we can sort of think what this is. Think about the form of the matrix. Let's now say that the matrix representation of this linear map T is now lambda 1, lambda sub 2, lambda sub n. Here's some arbitrary elements above the diagonal and 0 below. So now we have this upper triangular matrix. If this structure is in play, what does that say about that sort of first entry? This is now a scalar times some vector will put us back into that same direction of, let's say, v sub 1. The fact that the first column has only one non-zero element means that the first vector of the basis is in fact a special vector, which is an eigenvector. That's how we defined eigenvectors, that we have this matrix times a vector is a scalar times that same vector. And here our scalar is lambda sub 1. Means the first vector of the basis is an eigenvector of t and actually has an eigenvalue of lambda sub 1. So we could say that we now have this lambda 1, lambda sub 2, lambda sub n, some star here and zeros here. One particular vector, eigenvector, that would make that true is just 1, 0, 0, 0. Really anything in that direction, or anything with the top coordinate non-zero and all the other coordinates 0, will satisfy this relationship. And that's now our eigenvalue-eigenvector relationship. But what do we know about real, or playing on a real vector space? Do we always have this as a possibility? No, there's sometimes that we can't even find an eigenvalue. And this structure is saying you definitely have a lambda sub 1. Meaning if you needed a counterexample, just think of a 2 by 2 matrix. And that 2 by 2 matrix now was maybe a rotation. And that didn't have any real eigenvalues associated with it. And so that would not have this upper triangular structure. And that's what we were really trying to conclude. But if this linear operator t has no eigenvalues, which is possible for real vector spaces, then it must follow that t has no upper triangular form for particular linear maps on real vector spaces. There are linear maps on real vector spaces that can be upper triangular, they can be diagonal, but we can't guarantee that we always have an upper triangular representation. That's really what's being stated here. Let's now look, and again, we're just sort of looking at some of these statements about eigenvalues and eigenvectors. Another one is proposition 16 in chapter 5, which says, now if t is a linear operator, and that linear operator on a vector space V has an upper triangular matrix representation, then this linear map T is actually invertible if and only if all the diagonal entries of that upper triangular matrix, what do you think needs to be true for all of those diagonal entries for this map to be invertible? They have to be non-zero. Not positive, not negative, just non-zero. So if T is a linear operator and has an upper triangular matrix representation, boom. then in general that means we're maybe on a complex vector space, but it could be real, but not all reals have an upper triangular representation, so we're making that assumption. Then T is invertible if and only if all the diagonal entries of the upper triangular matrix are non-zero. So if you can find an upper triangular matrix for your linear map, and there the diagonal elements are staring you in the face, if all of those are non-zero, then that map has an inverse. If you have a 0 sitting there on the diagonal, then you can't invert that linear map. That now leads us into one of the most important properties in chapter 5, or results. So proposition 516 leads to one of the key results in chapter 5, which is labeled proposition 18 in chapter 5. Here, we're given a linear operator T, and we're assuming that that linear operator, which has an upper triangular representation, on some basis. Then we can actually say a little bit more about what those diagonal entries are. They're actually the eigenvalues. The eigenvalues of T are the diagonal entries of that upper triangular matrix. If you now have an upper triangular matrix, you have a lot of information. You can immediately start concluding whether or not that map is invertible. You can say something about, you now know all the eigenvalues, and the eigenvalues, depending on what application you're dealing with, provide you with a lot of good information. In a control setting, they tell you, depending on if you're in the continuous time or the discrete time, you're going to be able to tell stability from those eigenvalues just by looking at those non-zero diagonal entries. Let's look at a proof of this. Let's now take V1 through V sub n as the appropriate basis, which now this is the ordered basis that produces an upper triangular matrix. So take V1 through V sub n as the appropriate basis. That is the matrix representation of T using that basis produces an upper triangular matrix. Now, let's take lambda, variable in our field of numbers, F. And let's look at a matrix representation related to T, but incorporating this variable lambda. Let's now look at the matrix representation of T minus lambda I under the same basis. And hopefully it's clear that that's now just going to subtract lambda from each of the diagonal entries and do nothing to the other parts of that matrix representation, because lambda now is on the, or scaling this identity matrix. So that now we can write this as lambda 1 minus lambda, lambda sub 2 minus lambda, all the way down to lambda sub n minus lambda. Still have those arbitrary entries above the diagonal and zeros below. And now let's remember eigensolutions are associated with what space? Where do your eigenvectors live in terms of a space? And so now if I had an operator or a matrix, A minus lambda I, and lambda was an eigenvalue, then we know what about the eigenvectors? A minus lambda I times that eigenvector, or just from the eigenvalue eigenvector relationship, we have AX is equal to lambda x. We push all that over to the other side, and we now have A minus lambda I times x is equal to 0. So now the eigenvector needs to live in the null space. So we know that these eigensolutions are associated with a null space, and in this case, it's going to be the null space of T minus lambda I. So the eigensolutions are associated with the null space of T minus lambda sub I. Which means we want T minus lambda sub I to be, now we have a non-trivial null space. Now that map is no longer injective, is it? So we want this map, T minus lambda I, to be non-injective. If that map was injective, then we would have a trivial null space. Otherwise, null space is trivial. But we can also go back and remember we have a relationship between things with respect to operators and this injective, surjective invertibility properties of a map. But also remember that for operators, if that operator is injective, then that's true if and only if the operator is surjective, which is true if and only if the operator is invertible. And now we don't have injective, so we don't have surjective and we don't have invertibility. So this is now equivalent to saying we actually want T minus lambda I to be non-invertible if it's non-injective. And now we can go back to some of our previous results where we said our system was invertible if what? All of those diagonal entries in an upper triangular matrix were non-zero. previous result shows that upper triangular matrices or the invertibility, let me say our previous result shows that upper triangular matrices invertibility if and only if non-zero elements on the diagonal. So if we don't want invertibility, then we need those diagonal entries to be 0. But those diagonal entries are now lambda 1 minus lambda. That needs to be 0. Lambda sub 2 minus lambda needs to be 0. So now the lambdas that cause that to happen are in fact the lambda 1s, lambda 2s, and lambda sub n. Thus, lambda is equal to lambda 1, or lambda is equal to lambda 2, or lambda is equal to lambda sub n are in fact, are the values that make t minus lambda sub I non-invertible, and hence are the eigenvalues of t. And we were trying to show that if we have an upper triangular matrix on the appropriate basis, then the eigenvalues are on that diagonal of the upper triangular matrix. And that's what we've now shown. Now, we've been talking about upper triangular. We could actually restrict our matrix discussion to being even more restricted than upper triangular. We were trying to find special matrices or nice matrices, and that said if we can have more zeros in that matrix representation, that's better. That makes it nicer. So we said, okay, now we've shown that we can actually have upper triangular matrices. We can actually go further. We can throw everything above the diagonal away in certain cases to become now just a diagonal matrix. And that's even more special. So let's now look a little bit at these new matrices, which again are simply matrix representation of linear operators, diagonal matrices. Diagonal matrices are a subset of upper triangular matrices where all the elements above the diagonal are also 0. We now have something like that, and we're not saying that all of those lambdas have to be non-zero. Some of these lambdas could be 0. Now, let's see if we can try to identify when these linear operators will produce a diagonal matrix. What did we learn about upper triangular? Whoops, that's not the one I wanted. That was pretty universal if we're dealing with a complex vector space, isn't it? If we have a linear map on a complex vector space, then we can find a basis that will produce a matrix representation that's upper triangular. That's not so restricted. That's not quite the case for a diagonal matrix. Here, let's now see what we have. An operator T on some vector space V only has a diagonal form with respect to, let's say, the basis V1, V2 up to V sub n, if and only if V1, V2, V sub n are in fact eigenvectors of that operator T. So if we have eigenvectors of our linear operator and they can actually form a basis for this vector space V, then we can use those eigenvectors to actually diagonalize this linear map or this operator. And what we can think of here is really how we built up, or how we were talking about, this matrix representation of an upper triangular matrix. We needed it to be some linear combination of the basis. But now if our basis vectors are eigenvectors, then they are now scalar multiples. So think about how we showed that the first column of this upper triangular matrix, or of an upper triangular matrix, implied that the first basis vector was in fact an eigenvector. Now we just want to extend that argument. Now a similar argument holds for all columns of a diagonal matrix. Now, what you don't want to be thinking is that every operator is diagonalizable or has a matrix representation that's diagonal. That's not true. Not every operator has a diagonal representation. For example, any operator that has fewer eigenvectors than the dimension of the system is not going to be diagonalizable. So any operator that has fewer eigenvectors than the dimension of the vector space. Will not be diagonalizable. Let's look at proposition 20. If T is a linear operator and let's say that this linear operator T has dimension V, so now just think V is 10th order or has dimension 10 just to have a specific number. Suppose T is a linear operator and has dimension V, distinct eigenvalues, then this linear map or linear operator T is in fact diagonal with respect to some basis. And now we're playing on the fact that all of these eigenvalues are distinct. They're not repeated. That's the key. So now we have, let's say, eigenvalues that are 1, 2, 3, 4, and 5, five-dimensional vector space. If we have distinct eigenvalues, then what do we know about the eigenvectors? From an earlier, maybe not today's lecture, but what did we learn about distinct eigenvalues of linear operators? Their eigenvectors, the associated eigenvectors, are linearly independent, aren't they? So now if we have five distinct, let's say we're living in a five-dimensional vector space, we have five distinct eigenvalues, that immediately says we have five linearly independent eigenvectors. Well, now if we have linearly independent eigenvectors in a five-dimensional space, by definition of them being linearly independent, they are spanning the space and they're linearly independent. That's a basis. There we have it. And that's the basis that we would need. Here's sort of a justification of that. Let's say now we are going to prove that. The hypothesis states that we have lambda sub 1, lambda sub 2, up to lambda of dimension V. Distinct eigenvalues. So lambda 1 is not equal to lambda 2, is not equal to any of those lambdas. Up to little n is what I like to say, but let's just call it up to subscript dimension V, whatever the dimension of our vector space is. That's given. We have a linear map or a linear operator that has little n distinct eigenvalues. That's the statement A. Now let's let V1, V2 up to V sub dimension V be the associated eigenvectors. The eigenvectors associated with these distinct eigenvalues. And as you just told me, once we know that we have distinct eigenvalues, we previously showed that the eigenvectors associated with distinct eigenvalues are linearly independent. Which now says this list, V1, V2, up to V of dimension capital V, 1 has length, that's our list, has length dimension V, and is linearly independent. And that's what we need to form the basis. Therefore, V1, V2, up to V of dimension capital V is a basis of our vector space V. And what did we need for a matrix to be diagonalizable? We needed the basis to be eigenvectors, and that's what we just showed. Requirement for a diagonal representation is a basis of eigenvectors, and that's what we just showed. Now, bear in mind that the converse is not necessarily true. Note that the converse is not true. Fewer than dimension V distinct eigenvalues does not mean that we cannot diagonalize the matrix representation. So fewer than dimension V distinct eigenvalues does not mean that there is no diagonal representation. For example, you could have a matrix -1, -1, -2, 0, 0, 0, 0, 0, 0. That's okay. That's a diagonal matrix with non-distinct eigenvalues, and that's a valid matrix. So the fact that you do not have 3 distinct eigenvalues doesn't mean that you can't diagonalize a 3 by 3 matrix. You might be able to if you have linearly independent eigenvectors associated with those repeated eigenvalues. You can diagonalize that matrix. Now, once we have all of that, I would just refer you to a very important proposition, which is proposition 21, and this now starts relating or showing equivalence of different statements. One about eigenvectors, about distinct eigenvalues, about a direct sum decomposition of your underlying vector space. And that's a nice result that you might want to sort of keep in your hip pocket. And that hopefully will say that's enough for chapter 5. You still have more to learn on your own. Look at the stuff dealing with real vector spaces. It's now not as nice to play in because you now know that you may not have eigenvalues even with real vector spaces. So we'll pick up with chapter 6 on Wednesday.